Okay, this is a short video about procedure number 6. Procedure number 6, we have a transistor amplifier shown as figure 9. And today you wouldn't find a discrete amplifier like this. Turns out that, as I mentioned before, transistors, there could be billions of them, hundreds of billions of them on an integrated circuit today. Let's take a look at what we got here. This is a proto board on top of another proto board. I'm using the bottom proto board as part of a trainer, and it's providing voltage for me for this top proto board, and the 12 volts in the schematic figure number 9 is being provided by the board here. Let's just see if we can see anything that's, identify what's going on here. First off, the little silver case thing is a 2N 2102 transistor, workhorse transistor for many years. There's two green capacitors, which are the input and output coupling capacitors for the amplifier. We like to take and block DC with capacitors. Capacitors will not allow current to pass through, so they block DC. But they also allow the AC signal, which is being inputted to the amplifier, to go into the base of the transistor. These red and black leads here are the input, and the red and black leads over here, let me just hit the camera, are the output. And the input is shown as a yellow trace on the oscilloscope, and the output is being shown as a green trace. The other resistors I used to bias the transistor. Years ago, when we had discrete circuits and so forth, people had to design these things, and of course today we have integrated circuits where we can program what the gain is. So it turns out that I'm going to take, and right now I've got a 1 kilohertz signal at 200 millivolts peak to peak going into this amplifier. So let's take a look at the output on the oscilloscope. So we'll turn our camera around here and take a look at the oscilloscope. I don't know how well you can see the colors there, but the smaller signal is the input, and the larger signal is the green one, the output. So what's happening right now is the gain of each channel, channel 1 and channel 2, are both set at 500 millivolts per division, and over on the right you might see the voltage there, the peak-to-peak voltage. I don't know how well we can see this, but it turns out that the channel 1 peak-to-peak is shown here. It says 240 millivolts, but it's probably more like 200 millivolts. And the output is looks like it's 2.35 volts. This guy here, amplitude of signal 2. So it turns out it's got a gain that's just about 10. And that can be set by design of the circuit. The signal generator is putting out a 1 kilohertz, as I mentioned before, so let me get this to be running, and let's show you what happens as I take and change the frequency. You'll see that there's more cycles, so I can go up in frequency. The gain doesn't change very much at all. Right now I'm up at 5 kilohertz, we'll say. Of course, I could set the oscilloscope and show fewer sine waves. Let's go back. Let's go back down the opposite way. And if I go down the opposite way, we'll go down to 1, then we'll go down. And now what happens, I'm down to 100 hertz, and you might notice that the gain, the green signal, yellow is still the same size, but the green's getting smaller. If I go down even lower in frequency, what happens is the green one's now disappearing, and here they are, they're almost about the same size at this point. I'm down to 20 hertz, and it turns out at 20 hertz, these capacitors, the reactance of a capacitor goes up inversely with the frequency, or I should say at low frequencies it goes to infinity for the reactance, at high frequencies it goes to 0. That's why it's let through the 1 kilohertz signal, and here at 20 hertz it's not letting through very much of the 20 hertz signal. So let's go back to the higher frequency that we had before, and we'll go up to 1 kilohertz, which is here. I have to change my oscilloscope to show you the individual waveforms, and here we are with our signal again. if I take and hit the button here, I can stabilize it. And the other thing I might want to do is take and make these guys overlay on one another. So I ask you to take and do this with Circuit Maker, just to give you a little bit of frame of reference. Again, with 200 millivolts in, my output is roughly 2.35 volts. So those are some of the values you should be looking for. In the experiment, so the gain will be close to 10. In the experiment, I then ask you to take and increase the input signal level. So let's take a look, and I'll go over here to my signal generator, and I'm going to change the amplitude to 400. I'll go back to the scope. You'll see the yellow signal will get bigger. And actually what's happened is I got to turn the gain down on channel 2 because it's off the scope face now. And again, we'll click this here. So now we discover that the input now is 400 millivolts and the output is 4.6 volts. Still gain about 10. If I go and change the input to 600 millivolts, and you should do this with Circuit Maker. So let me go up to 600 millivolts here, and I go to 600. I'll take and click the scope, and now what happens is my input is 600 millivolts peak to peak. My output's about 6.77 volts peak to peak. Let's go up to 800 for the input. Go to 800, hit the scope, and again now we're starting to get, so I'm going to go drop this down to, let's make this 1.5, and yeah, we should be able to stop it there. So now we take a look, and we have about 800 millivolts for the input peak to peak and about 8.9 volts for the output. So I'm going to move it up to 1 volt for the input, 1 volt peak to peak, and hit my scope. And now you might notice something. The very bottom of the waveform down here, if you take a look, the very bottom of the waveform is kind of getting a little distorted. It turns out all amplifiers have a maximum input you can put in. It's called their dynamic range, and we're starting to overdrive it. So the last one in the little chart is 2 volts. I'm going to bring that up to 2 volts peak to peak, and now I'm going to take and run this, and interestingly enough, I'm going to have to take and change the gain. So let me kill that, and what you see now is the input, still a nice yellow sine wave going in, but the green output waveform is quite distorted. We are overdriving the transistor past its saturation value, it's called, and cutoff value. And if you listen to this on a loudspeaker, you would discover that you'd hear a lot of distortion at this point in time. As you'll learn with Fourier analysis, the sine wave is a single frequency at 1 kilohertz, but now that output is almost like a square wave, and it would have odd harmonics. You've created, by overdriving the amplifier here, new frequencies which weren't there in the original signal. We call that total harmonic distortion. So that's about it for this one.